We're going to start chapter 10. We're not doing section 10.1. That's all about calculus and conic sections, which sounds exciting, but is not on our AP test. So we're going to focus on parametric equations. We actually started off the year with parametric equations. We just didn't call them that. So parametrics are all about particles traveling on a curve. Our curve in the beginning of the year was not a curve, it was a straight line. We had a particle moving along the x-axis or a particle moving along the y-axis. So in the beginning of the year, we were just going horizontally or vertically. Now, both x and y will be changing, and x will control the left and right movement of the particle, and y will control the up and down. Also, at times, not so much for the actual AP test, but if you're trying to kind of check graphs and see what's going on, you might want to switch your calculator. Only if you're trying to graph a parametric, you might want to switch to parametric mode. Doing that changes your y equals so that you can see you have an x1 of t and a y1 of t. And so we'll get into that in a minute. So t is the variable in charge here. So x and y are talking about which direction the particle is moving. T is time, and t is the parameter. So when we write both x and y as functions of t, then you get parametric equations. And what we're looking at is the path of this particle on the x and y plane. So it's called a plane curve. To sketch a plane curve, the easiest thing to do is just set up a table of points. So you still have an x and a y axis. And you can see we're looking at t values between -2 and 3. So even though t is usually, we think of it as time, you can still think of time being negative if you're saying like wherever our starting point that we were looking at, t equals 0, we can go 2 seconds before that, 3 seconds after that. All right, so I'm going to just make a table here. So let's say t is 0. What would that make x? And what would that make y? I think it's helpful to write it out rather than do it in your head and plot as you go, because it can get easy to kind of make a mistake. So if you plug in 0 for t, sorry, I meant to put x and y up here. If you put in 0 for t, you would get -4 for x. And, this should say, we can't have x equals and x equals. This should say y. Make that correction. So you get -4 for x, and y equals t over 2, so you get 0 for y. And if I plug in, we're supposed to go between -2 and 3. So let's also go in the negative direction. If I plug in -1, I would get -3, -1/2, -2. I would get 0 and -1. And then, sorry, I kind of went out of order here. And then if I go back to the positives, starting at 1, I've got -3 and +1/2. Plug in 2, you get 0 and 1, and finally plug in 3, and you get 5 and 3 over 2. Now, in our textbook homework, they do not tell you which values of t to plug in. So I always plug in, I just start at 0 and go positive. And then if I'm curious about it, or if I'm checking on my graphing calculator and seeing that I'm missing something, I also look at what's happening on the negative side for these graphs. So it's not like t has to start at 0. They don't usually give you restrictions in our textbook homework. Go ahead and plot these points. So it doesn't really matter what order I plot them in, but I will label them with what their t is. So -4, 0. It's right here. That was t equals 0. And then -3, -1/2. That was t equals -1. 0, -1. That was t equals -2. And then -3, +1/2. T equals 1. 0, 1. T equals 2. And finally, we had 5, 1.5 right there. So when you draw in this curve, I'm going to connect all these points. Now, since we were given a restricted set of t values, I'm not going to continue this on. in tonight's homework, since we're not given a set of t values to plug in, t could technically be anything, so I would extend this further on and just show the values for which I plugged in. We also need to put directional arrows or orientation arrows saying which direction is this particle traveling. So having the time in there is helpful to show, but putting arrows in just kind of on each little section, this is supposed to indicate the path that the particle is traveling. So it's traveling along this curved path here. Sometimes we will want to eliminate the parameter. Remember, the parameter is t, so get rid of t. This would be used to help us graph. So the parameter, we would still need to know which direction the particle is traveling. But if I take these same two equations that we just graphed, this looks like a sideways parabola, right? Kind of behaves that way. It looks symmetric. So we can kind of verify that. So how do you eliminate the parameter? You solve for t in both equations. And then you can use substitution. When you have t equals and t equals, you can put those equations together and figure out what your equation is in terms of x and y. So the goal here is just to have only x and y's. We call this a rectangular equation. A rectangular equation, those are the equations we're used to, where all the ordered pairs are just x, y. So it would look something like this. We could say that, let's just solve this simple equation over here. 2y is equal to t. Rather than solving the other equation for t, I can just use substitution here and say if t is equal to 2y, then x is equal to, instead of t squared, make that the quantity 2y squared. So x is equal to 4y squared minus 4. And, excuse me, it's been a while since, excuse me, it's been a while since we did conics in both Math 3, Algebra 2, or pre-calc. But if you remember kind of vaguely, a y squared is a parabola that opens sideways, and when y squared is positive, that parabola does open to the right. So parabola opens right. And if you really remember some good stuff, remember this is like x minus h, y minus k. So it does have a vertex of negative 4, 0. So that checks out with what we just graphed up here. Parabola that opens to the right with a vertex of negative 4, 0. You don't have to identify all of that on the AP test. It's just kind of good to see the connection. All right, what about our second example? So there are a few ways to tackle this. I'm noticing that I could maybe, the y equation has 2 t's in it and the x equation just has 1. So maybe I want to manipulate the x equation. Maybe I want to say, let's start solving for this t. So square root of t plus 1 equals 1 over x. And I could square both sides. And I could solve for t. 1 over x squared plus, plus minus 1. And you could make that 1 minus x squared over x. It doesn't really matter. If I just leave it as it is, then I can use substitution up here and say y is equal to 1 over x squared minus 1, that's t, over 1 over x squared minus 1, and then there's a plus 1. Okay, so those aren't really there. And then I could multiply, get rid of the complex fraction. Multiply by x squared over x squared and distribute that through. 1 over x squared times x squared is 1. 1 times x squared minus x squared over 1 over x squared times x squared is just 1, so I'm not going to write over 1. So this shows me that if I were to make a table and graph based on t and graph the x, y ordered pairs for t greater than negative 1, I would get a parabola that has a vertex of 0, 1, and it opens down. What about this restriction, though? If t has to be greater than negative 1, what does that say about x? If I can only plug in t values bigger than negative 1, Now t doesn't have to be a whole number, but if I just pick 0, that make it 1 over 1. Even if I pick anything, negative 0.9, this is 1, a positive 1 divided by a positive square root. Restricting t to be greater than negative 1 ensures that this is a real number. X is going to be positive no matter what. And for y, what about y? If we're plugging in something bigger than negative 1, like 0, we could get 0. If we plug in like negative 1/2, we're getting negative 1/2 over negative 1/2 plus 1. Let's see, negative 1/2 over positive 1/2 would still give me negative 1. So it looks like y could come out to be negative still. So it doesn't seem like there's a restriction on our domain. Let's see, if we had like negative 0.9, it'd be like negative 0.9 over positive 0.1. So that's a pretty small decimal. So yeah, so I don't think we have a limit to our range for those, but we do have a limit for our domain. So I'm going to say y equals 1 minus x squared, but we're only plugging in x values greater than 0. It would be a little parabola that like has this 1, 0, but we're only looking at this side. Okay. What about, let's see. Oh, this is a different example. So first of all, things are not in terms of t, they're in terms of theta. And theta is restricted between 0 and 2 pi. But it doesn't really help us to solve for theta, like say arc cosine of x over 3 equals theta, because arc cosine is not a nice, easy graph, arc cosine and arc sine. The combination of those two don't have a nice, easy rectangular graph that we can think of. But I do want to isolate the cosine theta. And I do want to isolate the sine theta. I can still work with cosine and sine by using Pythagorean identities, and I'll be able to eliminate the parameter. So I remember the Pythagorean identity that cosine squared plus sine squared theta equals 1. And so if I replace cosine squared with x squared over 9 and sine squared with y squared over 16 equals 1, I get a rectangular equation that does not have theta, which is the parameter in it. And I also remember that that's the equation for an ellipse. Okay, last idea for today. How do we determine if we have a smooth curve? So like we just graphed this one and just kind of assumed that this was a nice smooth curve here. We verified it with a rectangular equation. I know that x plus 4 equals 4y squared is a smooth sideways opening parabola. What if it's not that obvious? So if we graphed it, is it smooth? So smooth, remember, means no sharp turns. We will be able to tell that a parametric equation or a curve is smooth on some interval if f prime and g prime are continuous on that interval and not simultaneously 0, unless that's happening at the endpoints. The endpoints don't matter. So what we're saying is, like if your interval is 0 to 5 and f prime and g prime are both equal to 0 when x is 2, then no, that's not a smooth curve. All right, so let's take a look. We need f prime and g prime. In this case, we need x prime, or remember, that's going to be dx d theta. Either notation is fine. So what's the derivative of cosine? Negative sine theta. And what's the derivative of y? What's y prime? That'd be dy d theta. Either notation works. I'm just putting that out there to remind you. 2 sine squared. So I'm going to use power rule first for sine theta. And then I have to use chain rule. The derivative of sine is cosine. All right, so are both of these functions continuous? We're on the interval 0 to pi. So sine is continuous. Sine, cosine are both continuous. No asymptotes to speak of. So both are continuous. So I'm just going to make a note, continuous. When is x prime equal to 0? So sine theta is equal to 0 when theta equals 0 and pi on that interval. But those are endpoints. So that's okay. And y prime is equal to 0. Let's see, sine's equal to 0 at 0 and pi again. And cosine's equal to 0 at pi over 2. But again, the endpoints are okay. They can have that in common. Cosine's equal to 0 at pi over 2. But since x prime was not equal to 0 at pi over 2, this is okay as well. So no, I'm just going to say same 0, meaning no simultaneous 0. So therefore, the curve is smooth. Let's graph it just to look at what this would be on our graphing calculator. So we say the curve is smooth. Let's type in for x1. This is cosine of t. Parametrics aren't going to put theta in. They're always going to put in t. It's fine. And then 2 sine squared, you have to type it in like sine theta, and then around that parentheses, square that. And if I just zoom 6, I can see kind of a smooth curve there. Zoom 6, I want to look at the window. What does that do? It starts t at 0 and ends it at 2 pi, which our interval was only 0 to pi, so we could switch this. Step size, I don't know what that is. That might be pi over 6 or something. So if we graph this, it's still a smooth curve. The fact that it didn't look any different means that when it was going from 0 to 2 pi, it probably traces over itself. Like it goes from one side to the other and then back again. So yeah, that's a smooth curve. Do the same thing for this one. So let's find x prime. I'm just going to write x prime this time. Power rule makes it 9 cosine squared theta. Chain rule says times the derivative of cosine negative sine theta. And what about y prime? Power rule, 9 sine squared theta. Chain rule times cosine theta. Now, when is x prime equal to 0? When theta equals, well, I have both a sine and a cosine. So when theta equals 0, pi over 2, and pi. Now, the endpoints don't matter, but this pi over 2 does. Because y prime is going to have the same thing. When is y prime equal to 0? It's got a sine and a cosine. It's equal to 0 at 0, pi over 2, and pi. Endpoints we don't care about, but right here. X prime and y, and not any, and y prime are 0 at pi over 2. So curve, the parametric curve, is not smooth. Remember, these two equations just tell you how is the horizontal direction changing at the same time as the vertical direction. So if we graph this one, we're just saying this is not going to generate a nice smooth curve. So this was 3 cosine of t raised to the third power. And this one was 3 sine of t raised to the third power. Graph it again. Yeah, so it's got this sharp turn right here. And that was, again, on the 0 to pi window. So you can't see it trace its path because it's too fast on mine anyway, but it almost looks like it's tracing over itself again. Anyway, not smooth. So we're going to stop it there for today, and your homework tonight is homework number 29.